In this video, I'm going to describe the pumping lemma for context-free languages. The pumping lemma is used in showing that some languages are not context-free. So it's used as a technique in a proof that some language is not context-free. There's a similar pumping lemma for regular languages, which is used to show that a given language is not regular. The two pumping lemmas are very similar, and in this video I'm discussing the one for context-free languages, which is a bit more complex than the pumping lemma for regular expressions and regular languages. Remember that the definition of a context-free language is any language that can be described by a context-free grammar. Here's a small example context-free grammar. It's got a number of rules, and in these rules we see non-terminals and we see terminal symbols. By convention, the first non-terminal on the first rule is the starting symbol. Non-terminals are sometimes called variables. The terminal symbols are symbols from the alphabet. In programming languages, the terminals are called tokens, and in natural language grammars, the terminals are words. The grammar is made up of a number of rules, which are sometimes called productions. The start symbol is oftentimes S, and our assumption is that the first rule identifies the start symbol. In this diagram, we're showing parse trees symbolically. Here's the starting symbol S for a parse tree, and down at the bottom, the leaves of the parse tree are labeled with the terminal symbols. And in this case, we are suggesting a parse tree for a string A, B, B, A, B, A. Remember what the definition of a language is. A language is a set of strings. The strings, each string is a sequence of terminal symbols, and it's a finite string. In general, though, the set of strings is infinite. So a language contains an infinite number of strings, but each string is finite in length. In the case of context-free grammars, we have a finite set of rules, but in general, an infinite set of strings that can be generated from those rules, which means we can have some very, very long strings generated. In some cases, the context-free grammar might describe a language with only a finite number of strings, and therefore we don't have really, really long strings. But any language with a finite number of strings in it is also a regular language, and so we're not really as interested in proving that that sort of a language is not context-free, because in fact it is context-free and it is also regular. Every regular language is a context-free language. So we're concerned with showing that languages are not context-free, which means they are, by definition, going to be infinite in the number of strings they contain. And so let's take a look at some really, really long string that is generated by the grammar. And here is the parse tree for that really long string. R and S are non-terminal symbols. And with a really long string, the parse tree has to be really big. And that means that on some path from the root, from the starting symbol S to a leaf, you've got to have one non-terminal appearing more than once. At least one non-terminal on at least one path somewhere has to appear 2 or more times. We can't have arbitrarily large parse trees with a finite small number of non-terminal symbols without having to reuse some of them somewhere. So the idea is, with a long enough string, we're going to have some non-terminal repeated on the path in the parse tree from the starting symbol all the way down to the terminal symbol. And that's what this idea is based on. Okay, let's take a look at a particular example grammar. Here we've got the language of strings 0, 0, 1 to the n, 2, 3 to the n, 4, 4. And here are some rules to generate this language. S goes to 00R, 44, and R goes to something containing R itself, or 2. And notice we've got recursion here. From the non-terminal R, we can generate a string that contains R. In some cases, the recursion could be immediate and direct, as it is here, or it could be indirect. So you have, for example, a non-terminal R going to some other non-terminal T, and then T going to V, and then V finally going back to R. But in any case, the key thing is that we have recursion in the grammar, direct or indirect. And it's from that recursion that we're able to generate really long strings. So let's take a look at some parse trees, or a parse tree for a particular string in this language. Here we've got a parse tree for the string 001112333R44. And you can see that we used the rule R goes to 1R3, 1, 2, 3 times. And finally we use the other rule, R goes to 2 at the bottom, to sort of end the recursion. Now I'm going to show my parse trees in this notation as well. It's a little bit more schematic. And the idea here is you can see S, and S expands to a bunch of stuff. In our particular example, it's 0, 0, but there's an R in it at some point, and there's a bunch of other stuff. So we don't really care what happens on the left side or the right side. We only care about this path that involves multiple R's. And we see that R expands to something, and somehow or other it ends in expanding to an R. And again, R expands to a bunch of stuff, R followed by a bunch of stuff. And finally, at the bottom of this parse tree, we see that R is expanding into just a string of terminals that doesn't involve R. The key idea here is that we can use the rule R goes to something containing an R more than once, and we can use it an arbitrary number of times. So here's our grammar again with our recursive rule R goes to something, R something. And here we see some strings that we can generate with this grammar. In this case, R expanded to nothing using the second, or expanded to 2 using R goes to 2. We didn't use the recursive rule at all. Here we used it once and we got 1, 1 and 1, 3. And here we used it 4 times. And we got a string 0, 0, 1, 1, 1, 1, and then the middle part, and then 3, 3, 3, 3, 3, and then 4, 4, the end part. So we're going to break these strings up into pieces called U, V, X, Y, and Z. The V and the Y part are involved with the R rule and the recursion part, so they can be repeated. So you can see that in this grammar, if we can allow U, V, X, Y, Z as a string that this grammar generates, we've also got to allow U, X, and Z where we don't use the recursive rule at all, and we can also use the recursive rule multiple times to get this string. So the idea here is that the string U, V to the I, X, Y to the I, Z is also in the language. Going back to the previous diagram, you can see that we use the recursion 1, 2, 3 times before we stopped with the basis case, but we could have used it 4, 5, 6, or even 7 times, or we could have used it 0 times using this parse tree that doesn't involve recursion way up here instead to get 0, 0, 2, 4, 4. So the idea is that with this recursion going on, the language is going to contain strings where the V is repeated and the Y is repeated. To say it again, for a context-free language, for any string that's long enough, some non-terminal has to be repeated in the parse tree. Okay? We've got to have a situation in any derivation where some non-terminal is going to a string that contains that very same non-terminal. So in long enough strings, we can break the parse tree up into something that looks like this, into this pattern. And if we can do that, then it's also true that the following kinds of parse trees are also legal. Here we've got a parse tree where the recursion is not used at all, so we've just got U, X, and Z. And here we've got a parse tree where the R is repeated twice, and we've got U, V, V, X, Y, Y, Z as a string. So U, V to the I, X, Y to the I, Z is also in the language. And remember that these symbols, U, V, X, Y, and Z, stand for strings of terminal symbols. They are not part of the alphabet directly. They are not non-terminals. They are representing strings of non-terminals. So in other words, to get long strings out of this grammar, we've got to use recursion in the grammar. So we have to have this sort of a pattern in any derivation of a long enough string. And finally, at some point, we're going to have this part of the derivation. This also has to be a legal derivation. So these are the parse trees that we see. We were able to derive something that contains an R from the non-terminal symbol R. And we've got to also be able to derive something that doesn't contain the R so that we can stop the recursion. So here is the pumping lemma for context-free grammars. This tells you what has to be true for a language that's a context-free language. For any string that's in the language that's sufficiently long, then it can be pumped. We say it can be pumped. Okay? And in particular, for any string that is longer than P, or equal to P, we're going to use P as the length called the pumping length, and every context-free language has a characteristic pumping length. We might not know what that length is, but there's a certain size above which any string has to have this property that it can be expanded, like we have seen before with R and recursion. Okay? So if the language is context-free, then there has to be a P such that for every string that's long enough, and by long enough we mean that it's at least P symbols in length, then that string can be pumped. That is, the V and the Y parts can be repeated. So the string can be broken into parts somehow. It might not be clear exactly how, but for a sufficiently long string, if it's in the language and the language is context-free, then we know that that string can somehow be broken apart into 5 pieces, and that all of the strings of the form U, V to the I, X, Y to the I, Z are also in the language. Okay, that the language must contain those strings as well. Now we've got another couple of caveats. In order for this to work, notice that V and Y have to be non-empty. At least one of them has to have some symbols in it. We can't get arbitrarily long strings using this pattern if V and Y are both epsilon, the empty string. And also, notice that we have to have a repeat before we get too long a space between the beginning of V and the end of Y. So the beginning of V and the end of Y can't be too far apart. And in particular, the length of the string VXY has to be less than or equal to P. In other words, it can't be any larger than P itself. So before we have P characters, we have to be able to find V and Y. Okay, now let's say the same thing again with a little bit more precision. Here is the lemma, the pumping lemma for context-free grammars. If A is a context-free language, then there is a pumping length. We may not know what it is, but it does exist. We'll call it P. Such that for any string in the language whose length is long enough, then that string can be broken into pieces and they can be pumped. And that string can be pumped. So for any string whose length is long enough, and by that we mean that it is greater than or equal to P in length, that string can be broken up into pieces somehow, into 5 pieces, which we'll call U, V, X, Y, and Z, in such a way that all 3 of these conditions down here are satisfied. Okay, the first condition is the main pumping condition, the one we're interested in primarily, and it says that not only is the string U, V, X, Y, Z in the language, but also any string of the form U, V to the I, X, Y to the I, Z is also in the language, including I equals 0, which means the string U, X, Z is in the language. When I is 0, V and Y disappear. And condition 2 says that Y and V and Y can't both be the empty string. There has to actually be something in those 2 pieces. So the length of V and Y has to be greater than 0. And the third condition says that we have to encounter this sort of thing before we get to strings that are longer than P. So the V and Y have to occur within P characters of each other. The beginning of V can't be too far away from the end of Y. Now we're going to use the pumping lemma to prove that languages are not context-free. So we're going to do a proof by contradiction. And before we get into the logic of how we're going to use these facts about context-free languages, I want to do a quick discussion of logic. And so let's start with a little bit of a refresher. Here is a statement in predicate logic. This is the for all symbol. So we're saying it's not the case that for all x something holds. And this is the existential quantifier. And it says there exists an x such that this condition does not hold. So we have the existential quantifier and the universal quantifier. And notice we have this property that if we want to negate a universally quantified expression, we can say it's equal to this expression. We can negate it by pushing the negation sign past the for all sign, and when we do that, we basically turn the for all sign into a there exists sign. And we can go the other way too. If we want to simplify an expression or rewrite an expression, we can move the not symbol past the there exists and convert it back into for all. And here we're going the other direction. We've got it's not the case that there exists an x such that something holds. That's equivalent to saying for all x, it's not the case that that holds. So down here I have a couple of examples. First example is of pushing the not sign through the universal quantifier. It's not the case that all numbers are even. Okay? It's not the case that all numbers, and here our condition is the property that the number is even. That's equivalent to saying there exists a number that is not even. Okay? It's equivalent to saying there exists a number, there exists an x such that x is not even. Now let's look at this one here. And my example is, it's not the case that there exists a green number. Okay, it's not the case that there exists a number that has the property of being green. And that's equivalent to saying all numbers have the not green property. All numbers, for all x, it's true that not green applies to them. And also we're going to be using De Morgan's law. So here's a refresher on that. When we push a negation symbol past a conjunction or disjunction into the subterms, we flip it from a conjunction to a disjunction, or from a disjunction to a conjunction. Remember that conjunction means and the symbol for it looks a little bit like the A in the and. That's how it's easy to remember. And the disjunction looks like a V. Okay, so this is De Morgan's law shown in one way. We push the not sign through the conjunction symbol, and it ends up down on the subterms. And as we go past the conjunction, we turn it into a disjunction. And likewise, if this had been a disjunction, we would turn it into a conjunction. Okay, now let's take a look at our pumping lemma and use the notation of first-order logic rather loosely to describe what we've got here. So the pumping lemma says that if we've got a context-free language L, then the following will hold. There exists a pumping length P. We don't know what it is, but we're just saying it exists. If the language is context-free, there's a length beyond which strings can be pumped. There exists a P such that for all strings in L that are long enough, okay, for every string in the language whose length is greater than or equal to P, then there exists a way to break that string into pieces, into 5 pieces, U, V, X, Y, Z. That's what I mean here. There exists a way to break that string up such that all the properties hold. The pumping holds, okay, U, V to the I, X, Y to the I, Z is in the language for all I, greater than or equal to 0, holds, as well as these other two conditions. The fact that V and Y can't both be empty, and the fact that the beginning of V and the end of Y can't be too far apart. Okay? So all of those hold. So again, there exists, for all, there exists, and then this and this and this. Now, what we want to do is we want to use the pumping lemma to show that a language is not context-free. So basically, we've got to negate this property and show that that holds. Okay? So what I've done here is I've just put a negative sign right here, a not sign, and then I simplified it by pushing the not sign in. So this existential quantifier will become a universal quantifier, and so on. And so putting the not sign in front of this whole pumping property, this is what we get. For all P, there exists a string in the language that's long enough, that's longer than P, such that for all ways to break that string into 5 pieces, it's true that none of those ways can be pumped. Okay, we got the not sign down here, and we turned this condition into a negated version of itself, this one into a negated version, and this one into a negated version, and we switched to or here. So for all ways of breaking up this string, it's the case that one of these conditions won't hold. Okay, either it can't be pumped or something's wrong here or here. Generally what we'll do is we'll basically assume that conditions 2 and 3, which are sort of not the meat of the pumping lemma, do hold. We assume that conditions 2 and 3 hold, and then we show that this condition 1 does not hold. Sometimes we can go straight to showing that condition 1 doesn't hold without and just ignoring these. Okay, because if condition 1 doesn't hold, in other words, if this is not an L, then we've satisfied the thing we're trying to prove. Okay? So it's a little bit confusing. We want to prove for a language that's not context-free that the pumping property does not hold. Another way to say this is this is a proof by contradiction. We're going to assume the language is context-free, and then we're going to proceed through the pumping property and come to a contradiction. I think it may be a little bit clearer to look at it this way. We're going to just take the language and prove that the pumping property doesn't hold here. But the logic of the string and the way we break it up is shown more precisely here. So now let's look at some. Okay, let's apply the pumping lemma to show that this particular language is not context-free. So that's what the pumping lemma is good for, to prove that a language is not context-free. So here's our language. We'll call it B. It's a bunch of A's followed by a bunch of B's followed by a bunch of C's, where the number of A's, B's, and C's is all the same. Okay? We want to show that this language is not context-free, so what we're going to do is we're going to assume it is context-free, but then show that the pumping property doesn't hold. And that's effectively a contradiction. If it is a context-free language, then the pumping property must hold. We're going to show that the pumping property doesn't hold, and therefore conclude that this thing is not a context-free language. So, going back to our logic, to show the pumping property doesn't hold, we say for all P. Okay, we don't know what the pumping length is, so we're going to just assume that it's P. Okay, we're going to call it P and not further constrain it, and say for all pumping lengths. Okay, and so we're going to let P represent the pumping length. Okay, we don't know what it is. Every language must have a pumping length. Okay, but we don't necessarily know what it is. So we can't really put any constraints on it. We'll just show that this holds for any P by not constraining it and simply calling it P. The next step is, in our negated version of the pumping property, is that there exists a string that's long enough. Okay, and that's the key. This is the key step, is finding your string that we're going to be able to use to prove that the pumping property does not hold. So in this case, we're going to use the string A to the P, B to the P, C to the P. This is in our language because the number of A's, B's, and C's is the same, but it's a very long string. It exceeds the pumping length. It's 3 times the pumping length in length. So this is a very long string, and while not knowing exactly what the string is, we can work with it symbolically. For any P, we can find this string. So now we have to look at all ways to divide this string up. For all ways to divide the string into the 5 pieces, we need to show that these conditions don't hold. Okay, so we can assume that the conditions 2 and 3 hold, and look at the other case. The primary case we want to look at is that the pumping part does not hold. Okay, so we need to look at all ways that we can break this string, our sample string, into the 5 pieces with V and Y. And we're going to break this into 2 cases. Okay? And the first case is that V and Y each contain only one type of symbol. And here are a couple of examples. V contains only A's, Y contains only C's. Here's another example. V contains B's, Y happens to be the empty string. So the second case is that either V or Y has more than one kind of symbol in it. And we'll look at that in a second. But in the first case of ways to break this string into U, V, X, Y, and Z, we're going to assume that U and Y each contain only one kind of symbol. And our case 2 will handle all other cases, namely where either V or Y or both of them contain 2 or more different symbols. Okay, so if this is, in this particular case, we'll have the fact that one symbol is always going to be left out. Okay, right? In this case, we left out B. V was A's, Y was C's. We didn't have any B's. One symbol is always left out. We can pump this string according to, we ought to be able to pump this string according to the pumping lemma and get something that's still in the language. And in particular, u v squared y x y squared z would add two A's and add an extra C. Okay? So at least one symbol is going to increase in number. Because V and Y both can't be empty, there has to be at least one symbol in V or Y. And so at least one symbol is going to increase in number. In this case, the A's and the C's increased. And because one symbol is always left out of this division, one symbol will not increase in number. In this case, B does not increase in number. So the string cannot still be in the form A to the n, B to the n, C to the n. And so in that case, in case 1, this string cannot be a part of the language. Now in case 2, we're saying that either V or Y has more than one kind of symbol. Okay, here's an example where V has A's and B's. Here's another example where Y has a B and a C. So now when we try to pump this string to, for example, u v squared x y squared z, we might not have the right number. We might have the right number of symbols, but the order is not going to be correct. Okay? In this case, y has a b and a c, and when we double y, we're going to get b, c, b, c. The symbols will not be in order. So no matter how we break that string up, we find that the pumping condition, condition 1, is not satisfied. Now, we didn't really talk about the other conditions. We don't really need to talk about the other conditions because we're able to show that condition 1 is violated in all these cases. But if you look carefully, we might be able to rule out some of these cases. In this case, the beginning of V and the end of Y are very, very far apart. And that would violate condition 1. But that's okay. We don't really need to worry about that. This is a better way. By ignoring conditions 2 and 3, we can really focus on the pumping part. And we don't need to use those other conditions in order to take care of all of our cases. Okay, now let's do a second example and show that this language, which we'll call D, is not context-free. D is the language of strings drawn from the alphabet of 0 and 1 that can be divided into two halves, and the first half is identical to the second half. So again, we're going to proceed logically the same way. We're going to assume that this language is context-free, and therefore it ought to have the pumping property. But we're going to try to show the pumping property and find that something goes wrong. We're going to find that the pumping property does not hold. And therefore, by contradiction, we're going to assume that this thing was not a context-free language in the first place. So, again, we can't constrain the pumping length because we don't really know what it is. Let P be the pumping length. There are no constraints on P, so we're showing it for all P. The next step is that there must exist a string of sufficient length. Okay, and so to show that there exists a string, all we have to do logically is just provide an example. We just have to give one string that works. We only need to find one string that works, that cannot be pumped. And here's a string that we're going to use in this example: 0 to the P, 1 to the P, 0 to the P, 1 to the P. Clearly the first half of this string is equal to the second half. And now we have to look at all the ways to divide S into parts, into 5 pieces. Okay, for all ways to divide this string S into 5 pieces, U, V, X, Y, Z. And we have to show that for each way, one of those conditions is not satisfied. we'll assume that condition 3 holds, that Vxy is not larger than P, and show that one of the other conditions fails. Okay. Okay, to analyze our sample string and to show that all ways of dividing it up violate the pumping property in some way or another, we're going to look at different cases. And we're going to focus on the boundaries between the zeros and the ones in our sample string. Okay, so our string consists of P zeros followed by P ones, followed by P zeros and P ones. And we're going to talk about the boundaries between the zeros and the ones and the zeros. And here's the midpoint of our string. Okay, and we're going to break this into several cases and ask whether Vxy straddles a boundary or does not straddle a boundary. Okay, so let's look at the first case where we assume Vxy does not straddle any of these boundaries. So here's a particular example where Vxy is just ones, but it could be just zeros or maybe just ones over here. Pumping up is going to yield a string with more ones in this particular case and an imbalance. By pumping up, we mean going from v to the first power to v to the second power or greater. Okay, so if we increase the number of v's and y's, we are going to get more ones. Okay, so now our string will look like this. It is p zeros again, but we have more than p ones in this section, and then we have zero p's and p zeros and p ones. So our midpoint has shifted, okay, into somewhere in the area of ones. So notice that the first half of the string starts with a 0. The second half of the string now will start with a 1. Okay, so the first half of the string is no longer equal to the second half of the string. So therefore, this string is not of the form WW, and it's not in the language. And so, since uv to the power 2 x, y to the power 2 z is not in the language, condition 1 is violated for this case, but we still have to look at the other cases. Okay, now let's look at the second case. And the second case is where Vxy straddles the first boundary. Okay, so here's an example. Here's our midpoint. Notice that Vxy cannot straddle the midpoint because we have p1s right here. So since this thing is p or less in length, it can't also include any of these zeros here. So now let's pump down. And this is a case where we can demonstrate pumping down. It's going to make the string shorter. It's going to make the first part of the string shorter. We're going to pump it down right here, and we're going to lose a few characters. Okay, that's going to shift the midpoint over here. And now we have a similar argument to before. The midpoint is shifted over here after we pumped down. And now notice that the first half of the string ends with a 0, and the second half ends with a 1. Okay, so this string is no longer of the form WW, and therefore it is not in the language. So we've handled case 2. The next case to consider is, I'll call it 2b because it's very similar. Vxy straddles the third boundary. Okay, and we can make a very similar argument that if we pump down, the string that we get is not in the language, and therefore the pumping property doesn't work for that case either. Okay, the last case to consider is that Vxy straddles the midpoint of our sample string. Okay, so because of the restriction of the second condition on the length of Vxy, or actually that's the third condition, we know that if Vxy straddles the midpoint, it can't also get into the first section of zeros or the last section of ones. Okay, it has to be somewhere in here. So pumping down will give us a shorter string. Okay, and it's not really clear exactly what our string is going to look like. And at first glance, it might not seem obvious that the string is not in the language. But what we've got is we've got a new midpoint here, and we've got p zeros followed by something that's less than p on this section and less than p in length in this section, followed by p1s. So we've reduced this middle section in length from 2p to something less. So our midpoint is now here, and the first half and the second half are each shorter. So now let's look at the first half of the string, and let's match it up with the second half of the string and see whether they are equal. Okay, the first half of the string, it has p zeros followed by fewer than p ones and ones. The second half of the string has fewer than p characters here, followed by p characters here. So if you think about it, there has to be an overlap between these zeros and these ones, and therefore the first half of the string cannot possibly be equal to the second half. And so again, we've shown that the pumping property is violated. So what we've shown is that for all the ways that we can break this string up into the 5 pieces, the pumping property will be violated, and therefore the pumping property can't hold for this language, and therefore this language is not context-free.